Good morning, everyone. Our final project is a Morris Worm Attack Lab. We used the Seed Labs internet emulator to recreate how a worm can exploit, copy itself, and spread through a network. Our presentation will start with a short overview, then explain the virtual machine setup, go through each project task, and end with our observations and conclusions. What is the Morris Worm attack? The Morris Worm attack is an attack where a malicious software spread automatically from one computer to another and operated without the need of a user to click or open anything. It was created by Robert Tappan Morris in 1988, a graduate student at Cornell University. It was one of the first major computer worms to spread across the internet. Morris did not intentionally try to create damage to computers, but since the worm automatically spread from one computer to another, it affected about 10% of internet-connected computers at the time. Even though it happened many years ago, many worms today will still use the same tactics, such as the WannaCry ransomware in 2017. This lab recreates the behavior of the Morris worm in a controlled environment. Instead of attacking real systems, we use the Seed internet emulator. The main ideas were exploiting a buffer overflow, copying the worm to a victim machine, and then allowing it to propagate across the emulated network. The Morris worm worked by finding vulnerable Unix machines, breaking into them, copying itself, and repeating the process. Historically, it used multiple entry points, including the send mail debug feature, the finger service, and password guessing. The important idea is that it did not stop after one machine. Once they reached a new system, it continued searching for more targets, which caused the fast growth. For the lab setup, we use the Seed Labs 2.0 virtual machine, which is based on Ubuntu 20.04. The lab files included Docker containers, container files, and the Seed internet emulator. Docker allowed us to run many simulated hosts and routers. To start the lab, we built and started the containers using DC build and DC up. These are the 6 tasks in the lab. We first got familiar with the setup, then attacked one target, added self-duplication, added propagation, prevented self-infection, and finally released the worm on the larger mini internet.
Alrighty, hey Professor, my name is Richard Perez and I am in your CSCI 401 class over the summer, completely online. This is the part I will be presenting for my group. So, task 1, get familiar with the lab setup. Task 1, get familiar with the lab setup. After booting the Docker container, we are able to connect the Nano Internet map in Firefox at the link in here. We then tested the Nano Internet by pinging 1234 on a host terminal, then typing ICMP and DST 1234 in the filter box of the map to see the ping. The bolded shapes are the host flashing. So task 1, observation. Because the Nano Internet is successful, launching a ping from one host and applying the ICMP filter makes the corresponding node flash on the map and therefore can visualize infected hosts. So task 2, attack the first target. We attack the first target container by exploiting a buffer overflow vulnerability in the server program of our Docker containers. We do this by modifying our worm code to generate, then send off a malicious payload to the target container. Task 2, we turned off address randomization and sent a test message to the vulnerable server on port 9090. We can see that the server terminal logged the input size, frame pointer, and buffer address of the test message. Then, we ran a script that must now be edited. We calculated the offset and suggested ret values using script from the math, then use the frame pointer EDP buffers address from the server log of the message. Here are the changes in the worm script, and here we provided screenshots, and yeah, thank you very much.
Hi, it's Noah. For task 3, self-duplication, with the goal to achieve self-duplication, we have elected for the second approach, which is to modify the worm to send a small payload that contains a pilot code, and then a larger payload with all the complicated stuff in it. The pilot code is the shell code included in the malicious payload for the buffer overflow attack. After the pilot code runs, it opens on a listener on the victim, allowing the attacker machine to send the larger worm.py payload. see, there's arrows included so you can see what we're directly talking about, but we modified the shellcode so the victim opened a netcat listener on port 8080, saved incoming data as worm.py. Then we modified the worm so that after sending the malicious bat file to the target, the attacker waits briefly and sent the worm to the victim's netcat listener on port 8080. You can see here, this is confirmation of it working. The server log says connection received. And then on the bottom, you can see that the victim container, that the worm successfully copied in. Just gonna skip this. For propagation, now that the worm can self-replicate, it must be able to crawl out and spread from our computer to the first target and then beyond. We can achieve this by making the getNextTarget function randomly generate an IP address, check if it's alive or not, and then launch the attack. From here, we can see that we made the changes that include modifying the programming to keep going after its first infection by including the and symbol. Then we had the getNextTarget randomly generate IP addresses with the nano internet candidate range, which you can see below as X between 151 and 155 and Y between 70 and 80. You can also see that this new function tests to make sure the target is online before the infection is attempted, and it pings the target once. If it replies, it attacks. If it doesn't reply, the worm will try another random IP. Then we commented out the exit function so that the program will keep going. In the red, we can see that the HTOP system resources look like while it's running the worm, very intensive. The Docker server console showing attack process in the blue, and the nano internet displaying the worm's progress as it moves around the internet. And that is all.
Hi, my name is Syed. So for task 5, now that the worm is able to self-replicate, we must make sure it doesn't attempt to infect itself. We do this by creating a function that checks to see if a path exists that indicates that a host has been hacked. To prevent self-infection, we added a check for the file marsworm_infected. If that file already existed, the worm exited. If it did not exist, the worm created the log file and continued running. This prevented multiple full worm instances from running on the same host. When the worm found an already existing log file, it printed a message and exited. We also manually checked an infected host and confirmed that the log file existed. This showed that future worm copies would detect the previous infection and stop, preventing many duplicate worm processes from being created on the same host. Task 6 was releasing the worm on the mini intranet, for which we had to switch to the larger mini intranet setup. For this task, we switched to the larger mini intranet setup. We changed the getNextTarget function's IP range to match the mini intranet. Then we used the file provided by the lab to start the larger number of containers. This took about 9 minutes. After releasing the worm on the mini intranet, the worm output showed it checking targets, finding live hosts, and launching attacks. The map in Firefox showed activity across the larger network, and HTOP showed the resource usage while the worm was running. Because the mini intranet has many more hosts, it used noticeably more CPU and memory than the smaller nano intranet, but also gave us a larger environment to test worm propagation. Overall, this lab showed how dangerous worms can be because they spread automatically after the first compromise. We saw that the worm could exploit a target, copy itself, and continue spreading to other reachable systems. We also saw that uncontrolled propagation can consume heavy CPU resources, especially when duplicate instances run on the same host. Adding the log file checking mechanism helped prevent repeated self-infection on the same machine. The Seed Internet emulator made the process easier to understand because we could watch the infection spread visually on the map. Thank you for watching.